Whoa, that was loud. My goodness. All right. What do we get when we do this little exercise here? If I integrate from negative a to a of x dx, I get 1/2 x squared from negative a to a. And if I plug that in, I get 1/2 a squared minus 1/2 negative a squared. And this looks like 1/2 a squared minus 1/2 a squared when we're done. And you can't just plug shit in because the infinity is going to change some stuff. Obviously, if a equals 1, the integral equals 0. If a equals any real number, the integral equals 0. What do you think 1/2 infinity squared minus 1/2 infinity squared equals? You want to say 0, right? Well, let me show you. You're not going to believe me, so I thought I'd load up something all the students like to trust. Switch cameras here. Wow. Now I can't make the desktop show the PC. That's funny. Oh, well, that's going to be missed on the recording. But you all can see it. It diverges. Infinity minus infinity are not, they're not numbers, so we can't subtract them. It's like a concept minus a concept. It's kind of meaningless. So there's no solution here that you're going to like. And I agree, that's some bullshit. It's recording the right thing. Let me make sure. Yeah, it's recording the right thing. So this is not the case for infinity. This diverges. I argued with my math teacher, Miss Keene, when I was a student here. I said, this is some bullshit. Because she just did the integral without pointing out all the middle ones. I'm like, if I fucking put in any other number, it equals 0. So like, that's just how mathematics works. In pure mathematics, they have countable infinities or infinities of different magnitudes. So I guess if you're going to make a concept like that, you might as well fucking double down on the concept. But that's what 7.8 is on, dealing with things that have questionable areas. We call them improper integrals. Improper integrals, type 1 has limits at infinity. And type 2 will have discontinuities or asymptotes. And how do we deal with that shit? So now that we got past the bullshit of infinity minus infinity doesn't equal 0 like every other number, let's just deal with it and we'll go on. Ainsley, did Tracy do this shit with you guys? Do like the integral of x and show that it equals 0 for every other value except for infinity? Oh, you would have, because it's a mind fuck. You're like, nope, bullshit. You might not have. You're a quiet one. I don't know. Did you ever call bullshit on No, you never did with me. You only do that outside of class. All right, looks like everyone's done writing. Let's talk about type 1. Type 1, we've got a couple formats for type 1. If I have like a going to infinity, f of x dx, we can rewrite this. I don't know how it helps, but we do. Rewrite this as limit of some other variable. I'm going to use t. As t goes to infinity, a to t f of x dx. We could also have negative infinity to b. And we'll do limit as t goes to negative infinity. T to b f of x dx. And for these, we say the integral converges if the limit exists. And diverges if the limit doesn't exist. And you might be in the habit of writing infinity as a limit, but like if your answer is infinity, the limit is dne. Which stands for does not exist. dne. Then we have one where it has infinities of both limits. Now, things on like ChatGPT, and I just had it up there, will show you limit as a goes to negative infinity, limit as b goes to positive infinity, a to b f of x dx. But this isn't really appropriate. Notation. We try to keep our limits just singly. So the way we deal with this, a better way, if you don't want to get made fun of by people in the mathematics field, is we will do, let me rewrite it and show what we're going to have it as. We're going to split it up into two integrals. We'll do limit as t goes to negative infinity of t to some constant a. And then plus the limit as t goes to positive infinity of a to t f of x dx. We've always been able to split up integrals like this. It's not just an infinity to infinity thing. Like if you had 0 to 2 f of x dx, this is always equal 0 to 1 f of x dx plus 1 to 2 f of x dx. And that red pen's dead. In this circumstance right here, both integrals must converge. Converge means like approach a value or real number. At least mathematically. In real world, like converge, if a flash mob, the people converge on a specific, they're all just kicking around doing different shit in the area, and all of a sudden they fucking converge on a location, the music kicks on and everybody fucking just starts dancing. That's converging also, but that's a different type of convergence. So let's look at some examples. Let's start with 0 to infinity, x over x squared plus 2 quantity squared dx. First thing we want to do, where's my other red pen? I like having red in my repertoire. We want to shift to using the limit notation. So we're going to say limit as a goes to infinity. You can pick whatever letter you want. I used t earlier here. I'm going to use a here. As long as it's not in the integral, you're good to go. 0 to a, x over x squared plus 2 squared dx. What will we do with that integral? What is looking good there? Looking like a u sub to me. I would say x squared plus 2. So du equals 2x dx. Or I could move the 2 over to the other side and make it a 1/2. And when x equals 0, u equals 2. When x equals infinity, infinity squared is still infinity. U equals infinity. You can choose to go back to x if you want later on, or you can just switch to using u. Infinity don't fuck around. Infinity just stays infinity. So if we do that, this shifts to, we still have our limit there. Can't get rid of it until we evaluate at it. We're just making sure the sign, like the infinity, doesn't change. So we're still going to go 2 up to a. That limit's still infinity, but since we're using a for infinity, that's what we're going to have up there. And we have got a 1/2. And 1 over u squared is u to the negative 2. So we go up the power, divide by the power. It would be a -1 up there, u to the -1 or 1 over u. Evaluated from 2 to a, and I need to put my limit shit out front, and I didn't give myself room. limit as a goes to infinity. And when we do this, we get limit as a goes to infinity of -1 over 2a minus -1 over 4. Now we can evaluate the limit with a on bottom. This goes to 0. We've got minus minus equals plus 1/4. Yeah. Yeah. So this converges. And when it converges, we say what the value is. Good question. Ainsley, you know my extra credit charity, as you call it, my Oprah charity on a test? Their question on their first test was take the first two derivatives of x, secant x, tangent x. So, which is fine for the first one. It's not too bad. You got 3 parts, but then it gets really fucking ugly. Second derivative. I bet a lot of you in here would fuck that up. It's not an easy one to do. A lot of moving parts. You just got to go slow. I bet you could. You just got to go slow. Next question. Let's do negative infinity to 0. Let's go, I don't know, x e to the x cube, or 1/3 x dx. So as you can see, we're going to rewrite that with a limit. I'll use t. Why not? Putting t to 0, x e to the 1/3 x dx. Maybe I'll write that as x over 3 because it looked like written wrong. How could I do this? Your inclination to try U sub is not going to work. I'll just tell you that right now. Who's been doing their homework? Do it by parts. And we follow the Liate, the algebraic thing comes first. We're going to let u equal x, so that du equals dx. And we'll say dv equals ex over 3 dx, so that v equals 3e to the 1/3 x. I've got uv, which is 3x e to the 1/3 x, evaluated from t to 0. Minus the integral of b du. Three e to the 1/3 x dx. We'll have limit as t goes to negative infinity. 3x e to the 1/3 x. That's going to pull out another 3. We're going to have minus 9e to the 1/3 x. Evaluated from t to 0. So if I do this, the one with 0 in it doesn't need to stay inside the limit. So I've got 3 times 0 e to the 0 minus 9e to the 0. And then we got minus, now we're doing our t1. So we're gonna apply the limit here. So this will be 3, not yet. Yeah, we'll apply the line here. 3 times infinity e to the negative infinity minus 9e to the negative infinity. And now we're like trying to figure out what's happening here. This one, e to the negative infinity, is 1 over e to the infinity. So this is actually going to 0. You have an infinite number on bottom, 1 over infinity. That's one of the things you learned in Calc 1. So this is 0. This is 0, and this is infinity. Infinity times 0, which one wins out? This is an indeterminate form. So what can we do with an indeterminate form and a limit? I'm going to go back up to here and do L'Hopital. I'm going to rewrite limit as t goes to negative infinity, 3x e to the 1/3 x. I'm going to rewrite this, swapping this, because if I make the t negative, if I make this negative, I can make this positive. Make x negative to make t positive. We've got limit as t goes to positive infinity, negative 3x e to the negative 1/3 x. And now I can rewrite this in a form that is L'Hopital friendly. Negative 3x over e to the 1/3 x. This is infinity over infinity, a nice little indeterminate form we can work with. So L'Hopital. When I use L'Hopital, I tend to write L''H to say that I'm doing it. So in the future, if we do L'Hopital, that's what I put. So this changes our limit. How does L'Hopital work? Just do the derivative of top and bottom separately, right? So the top is negative 3, the bottom is 1/3 e to the 1/3 x. And now if I evaluate at infinity, I have negative 3 over infinity, which is 0. Which meant this equaled 0. 0, 1 out over infinity. And that's 0. In fact, only one of these is not 0. That's minus 9. So our integral from negative infinity to 0 of x e to the 1/3 x dx equals -9. You guys ready for the next one? Nope, I see it's still going. Everyone ready? Nope, I still see a pink on. Patience, Jones, patience. All right, I don't see anyone writing now. If you need it out longer, say something. Otherwise, we are going to dive into the madness that is negative infinity to infinity, x cubed e to the negative x squared dx. Yeah. I'm going to break this up into two integrals and put my limits in. So I'm going to do limit as a goes to negative infinity. I'm going to do a to 0. 0 is a nice value for the exponential to have there. Makes calculating the exponential really easy. And then we're going to have the limit, we'll use b on this one, to positive infinity, 0 to b of the same integral. So what's something that you guys are interested in trying? I kind of want to like get rid of the x squared and the exponent. Let's try saying u equals x squared. Let's not fuck with the negative sign for now. So du is going to equal 2x dx, or 1/2 du equals x dx. Which means my limits are going to, I'll have limit, and I'll look at the limits in a second. Well, let's look at the limits now. When x equals 0, that's on our list, u equals 0. When x equals negative infinity, we're squaring it, u is going to be positive infinity from the squaring. And when x equals positive infinity, u is still positive infinity. So a is changing limits on us. And this x cubed, I can split that up into x squared and x dx. So this gets eaten up with a du, and x squared is u. So we have u e to the negative u du plus the limit as b goes to infinity of 0 to b. U e to the negative u du. Again, this is an integration by parts. Since I'm already using u, I'm going to use w and v. So integration by parts. I'll say w equals u, so dw equals du. And dv equals e to the negative u du. So v equals negative e to the negative u. As a goes to infinity, wv is negative u e to the negative u, evaluated from a to 0, minus the integral of v du. V has a negative in it though. And b is going to look the same. I'll just change that to a plus now. And to make this a little bit easier, let's address these real quick. So these are negative u over e to the u. And if I'm doing the limit as a goes to infinity on that from a to 0, I have negative 0 over e to the 0 minus a negative a over e to the a. So when we apply the limit here, I didn't leave room for the limit again. Limit as a goes to infinity. This is 0 over 1, right? So that's 0 already. This is going to be infinity over infinity, but we just saw with L'Hopital. We did it right now. We'll do it again. This will be 1 over e to the a. And this equals 0. So both of those are 0. I'm missing a 1/2. I'll put the 1/2 out front. That way we didn't need it in any of our calculations. And if we look at the B, it's no different. Limit as B goes to infinity. When we do this, we have the B one comes first, so negative B over e to the B minus or plus minus a negative, which is plus 0 over e to the 0. And we're again doing limit as B goes to infinity. L'Hopital, this is 0 already. L'Hopital on that is going to make it -1 over e to the B. And this is just 0 also. So both of those are 0. All we have left is the two integrals I hadn't worked on yet. So we've got 1/2 the limit as A goes to infinity. These two are positive. We've got A to 0, e to the negative u du. And I've got plus 1/2 limit as B goes to infinity. 0 to B, e to the negative u du. Because we saw that both of these were 0. 0, 0. All right, we're on the home stretch. 1/2. When we integrate both of these, they're going to end up with a negative. Let's just put the negative out front and not fucking deal with it for now. We've got limit as A goes to infinity. E to the, fuck it, I'm going to write it as 1 over e to the u. A to 0 plus limit as B goes to infinity. 1 over e to the u, or yeah, 0 to B. And we have our -1/2 out front. Did I fuck anything up? Good to go, other than that 1/2 that I left floating for a while. So we have -1/2, 1 over e to the 0 minus 1 over e to the infinity as I evaluate the limit. Then plus 1 over e to the infinity minus 1 over e to the 0. So this is my 0 to A, or A to 0. And this is my 0 to B. With the limits evaluated, this goes to 0, this goes to 0. 1 over e to the 0 is 1. I got 1 minus 1 in there. That whole thing evaluated to 0. And let's take like a few minute break before we start type 2. Pause the recording, give you a chance to stretch or use the restroom. So now we'll look at the type 2 ones that had like discontinuities and shit in it. Let's take a look at, I don't want to say this. Do I want to give a list of shit? That's I think it's easier to show by example. So let's do the integral from 0 to 2. 1 over the square root of 4 minus x squared. If I were to plug in 0 right now, this is a valid answer. 1 over square root of 4 is 1/2. If I plug in 2, I get square root of 4 minus 4 on bottom. Square root of 0 is bad juju on the bottom. So the way we deal with this, and thinking about how we're doing it, this is like having a quarter of a circle here. 0 to 2, or x equals 0 to x equals 2. Because if I said y equals the square root of 4 minus x squared, y squared equals 4 minus x squared. So x squared plus y squared equals 4. This is a circle, but we have a positive y, and we're only doing 0 to 2, which would be this region. So the way we address it is we put in a dummy variable. I'll do t. And we're not doing the limit of t equals 2, but we're doing limit as t approaches 2 from the left. It's not a full limit. It's just a one-sided limit. So one-sided limits at discontinuities if it's at the boundary. Nope, period. One-sided limits at discontinuities. Discontinuities. This will go from 0 to t. 1 over square root of 4 minus x squared dx. Now, if I don't treat that as a circle and I treat this as a triangle here, I can make my hypotenuse 2, if this is my angle, and this would be, I'll call that x and I'll call this y. Because we saw this before. When we had a perfect square minus another perfect square, this led to doing sine inverse or sine. We wanted to use sine. So if I say from my triangle, sine theta equals opposite over hypotenuse, x over 2. So x equals 2 sine theta. Dx equals 2 cosine theta d theta. Do you guys want to take a look at our new limits now or put x back in later on? I'll let you guys pick. Change the limits or go back to x? Change the limits. Selection made. So when x equals 0, we're saying sine of 0 or sine of theta equals x over 2, or I'll take a look at this form. Actually, we can do theta equals sine inverse of x over 2. So we have theta equals sine inverse of 0 over 2. Where does sine equal 0? What? Well, it does at pi, but that's not in the range of sine inverse. It's also at 0. And if x equals 2, then we've got theta equals sine inverse. And we're approaching from the negative side. 2 over 2. That's a 1. So we're really going, where does sine theta equal 1? at pi over 2. So what happens to our formula? We have limit as t goes to the 2 minus turns to pi over 2. We'll say it's coming from the minus because we're rotating around to it. Integral of 0 to t. The top is 2 cosine theta d theta. That was my dx. My bottom is x squared is 4 sine squared theta. That's just doing the substitution without cleaning anything up yet. So 2 cosine theta on top. I can factor out the 2. This is 4 times 1 minus sine squared, which is 4 cosine squared. So if I do the square root of that, this is really just 2 cosine theta on bottom as well. So this gets really easy. We're going from theta from 0 to t. We plug it in, we've got t, but t is pi over 2 minus 0. It's just pi over 2. So all of these have converged so far. That's good. You guys ready for another? See a couple pins still going. Nope. Oh, I just, yeah, some people still writing. Hold on a second. All right. So next one. Let's do 0 to 2. 1 over x minus 1 to the 1/3 dx. We can look at this as is or do a u sub to make that bottom look prettier. What would you guys like to do? Leave it as is or do a u sub? What? U sub. All right. So we'll do a u sub, u equals x minus 1. So du equals dx. When x equals 0, u equals -1. when x equals 2, u equals positive 1. And I have the integral from -1 to 1 of 1 over u to the 1/3 du, or -1 to 1 u to the -1/3 du. Now, this is going to look a little like 1 over u does some shit like this, and doing the cube root really doesn't change it a whole lot. Well, other than making it look good. And if we're doing -1 to 1, we're looking at this region right here and this region right here. We have a discontinuity at 0. At u equals 0, not x. If we did it with x minus 1, we'd just have to shift over that discontinuity, but it would still be in the middle of the range, which means we have a fucking problem in the very middle of our integral. So we're going to deal with this by switching this into two limits, or two integrals. We'll do the first part's going to go from -1 to 0, u to the -1/3 du, and I'm leaving some space because I'm going to change that 0 to look like something else. And then plus 0 to 1 u to the -1/3 du. And now, since we have those discontinuities there, I'm going to make this look like limit as a goes to 0, and this is going to be from the left side. I'm going to change that to an a. And this will be limit as a goes to 0 from the right side with an a down here. So we're doing a here, and the -1 to 0 is approaching it from the left, which is why we have the negative sign. And 0 going to 1 is approaching it. The 0 is coming in from the plus side. All right, up in power, we go up to u to the 2/3. Divide by the power, puts 3/2 out front. And we have limit as a approaches 0 from the left. -1 to a. Plus limit as a approaches 0 from the right. It's the same damn integral. So 3/2 u to the 2/3 here from 0 to a. Or a to 1, sorry. And what was once a problem is now no longer a problem. We can actually plug in the 0. So I have 3/2, 0 to the 2/3 minus -1 to the 2/3 plus 1 to the 2/3 minus a, which is 0 to the 2/3. So you might be going, well, what the hell is going on with this? -1 to the 2/3 is the cube root of -1 squared. And this is the cube root of +1 squared. So I've got negative plus like that. The zeros we don't need to worry about. There's a 3/2 out front still. That still matters. But what does this equal on the inside? If I square this, I got 1, and the cube root of 1 is 1, but there's a negative sign out front. And this one, I square it 1, cube root is 1, but that's a plus. And this is going to 0. Did I do something wrong, Dad? You're biting your lip. You can just process it. All right. More. We gotta do one more. I don't see anyone writing, but I'm gonna make sure. Are you good, Joanna? Okay. If you need this up longer, say something. Let us do the integral from 6 to 8. 4 over x minus 6 cubed dx. If you didn't like the -1, you probably, or x minus 1, you probably don't like the x minus 6. So let's just do a u sub and get that shit done with. When x equals 8, u equals 8 minus 6 is 2. When x equals 6, u equals 0. So we have the integral from 0 to 2 of 4 over u cubed du. Or if you want to write that in a form that's easier to integrate, we'll make that a negative exponent right away. And we're like that. We have an issue here at 0. So let's rewrite this with limits. I'll say limit as t approaches 0. And since we're going from 0 to 2, as we're going to it to the left, we're doing a one-sided limit with 0 positive. T to 2, 4u to the -3 du. So we go up a power is -2, 4 over -2. We're looking at the limit as t goes to 0 plus of -2 over u squared. This might be easier to look at that way. And we got a t and a 2. So I've got -2 over 2 squared minus the limit as t goes to 0 of -2 over t squared. So I've got -1/4. And then what happens when I do the limit here? Two over 0 is what? Or 2 over something approaching 0? It's infinity. So the limit or the integral diverges. No solution to this. Yeah. Yeah, I see what you're saying. Thank you. Don't know why I pull the scrub move. Now, in the previous problem, we saw that we had 1 over u to the 1/3, and this converged to give us an answer. And here we had 1 over u cubed, and it diverges. In the very near future, we'll look at 1 over x to the p dx, and we'll have like a limit at infinity, and we'll see what values of p converge and what values of p diverge. Actually, Bucky, we'll do it now. We got time. So rather than making you wait for the punchline, let's just do it now. So I'm going to rewrite that. Doing that right? In something to infinity. Yeah, 1 to infinity. So infinity is causing a problem. I'm going to change that to a t. Limit as t goes to infinity. Integral of 1 to t. 1 over x to the p dx. Or limit, if it helps make it a little bit easier, 1 to t x to the negative p dx. So if I go up a power and I don't know what the value of p is, I can't really put a number there, but I can say negative p plus 1. Right? And then we would divide by the power. I'm going to put that out front. And I'm going to rewrite that as 1 minus p. And we're doing the limit as t goes to infinity of 1 to t. So when I write this out, there's no p in the limit, so I'm going to move that 1 over 1 minus p out. And I've got limit as t goes to infinity this is x to the 1 minus t. I'm sorry, t to the 1 minus p minus 1 to the 1 minus p. This might help you see, this is gonna be a one for pretty much any value, right? Any value P, this should be one. One to any power is one. So how can I look at the limit of one minus or T to the one minus P? Do you guys know how we can rewrite that? We can rewrite it as something we recognize. Yeah, I can write this as T times T to the minus P. Which still are limits there. So I've got 1 over 1 minus P limit as T goes to infinity. T over T to the P. Well, negative P moving it to the bottom makes it positive P. Oh yeah. Then we got a -1. So we don't have any problem with divergence here. On the one. What values of P are going to fuck this up? So we got to think when does this diverge? It's going to diverge if this overall thing has a value where T is got a positive exponent, right? So if I have a positive exponent and I have infinity there, it fucks it up, right? So we want this to not be a positive exponent. So P actually needs to be smaller. If P is between 0 and 1, ooh, equal portion. Yeah. Because if we do it like this, it's T over T at 1. But before we do that, we don't know what the P is. This is supposed to be divergent. And P greater than 1 converges. I want to say it. That doesn't sound right now that I'm looking at it.
Oh, we don't have to worry about P1 because it has
Oh, P can't equal 1 because of this, right?
the domain.
P equals 1 is going to fuck that up. I knew there was a reason why fucks this fraction up. That's why we're going to include that in the divergent category. This is actually, we're going to see this later on in chapter 9, which we're starting next. We're going to go back to chapter 8 later on. When we start doing sequences and series, this is called a P series. So we'll see that one again. And chapter 9 is all about convergent and divergent shit. Is it your favorite chapter, Ainsley, in Calc 2? Is it your least favorite? It's my least favorite too. You're not gonna enjoy the convergence and divergence test. I'm probably, if it makes you feel better, I'm not gonna enjoy teaching them either. So this is just like a group torture fest that we're gonna do for, 1 to 2 weeks when we're doing it. One more thing for today. But to get to it, I need to tell you about, talk about convergence for doing our comparison test for improper intervals. So comparison theorem for improper intervals. We are going to assume that 0 is less than or equal to g of x, which is less than or equal to f of x, for all x greater than or equal to some value a. So pictorially, what does that look like? We've got, it doesn't really matter what happens to the left of a, but at a, g of x is always lower than f of x. We'll have some cutoff here at a. Now, they could have met, they could meet right here. They could meet and f of x could be lower on the left and higher on the right, but it doesn't matter. We're doing greater than a. So if we're looking at the integral of a to g of x, or a to infinity, sorry, f of x, I said let's start with g of x. Let's do g of x first. If this diverges, then the integral of f of x is even bigger than a to infinity of f of x also diverges. And if we had a to infinity of f of x dx, if this converges and the area of g of x is going to be lower than it, but still like this, because g of x is always greater than 0, so it never goes negative, then g of x converges as well. So let's do one, I'll do a generic example before we get to the cool one. Let's say we're doing 0 to infinity of e to the negative x squared dx. And it might be steeper than that, but that's the general shape. At x equals 0, crosses at 1. I can even split this up into two regions. I can go like 0 to 1 of e to the negative x squared dx plus 1 to infinity e to the negative x squared dx. And this is 0 to 1 is a finite area. This is a finite value. It exists. The question is, what about this? And the reason why we want to go up to 1 is because let's take a look at it. Like if x equals 2, this is e to the negative 4. Or 1 over e to the 4th. Right? Because we're squaring the x. So what if we compare this? How does 1 over infinity e to the negative, well, how does e to the negative x squared compare to e to the negative x? For x greater than 1. Well, e to the negative x, this is e to the negative x squared. E to the negative x would be 1 over e squared. One over e squared is bigger than 1 over e to the 4th. The bigger the denominator, the smaller in value it is. So we're going to compare this, compare to e to the negative x. And e to the negative x is always bigger. So if this converges, so does e to the negative x squared. So this will be the limit as t goes to infinity. 1 to t e to the negative x dx. When we integrate that, we've got negative e to the negative x from 1 to t. Which is the limit as t goes to infinity, negative 1 over e to the t plus 1 over e. As t goes to infinity, this goes to 0, and we have 1 over e, which converges. So by comparison, so does e to the negative x squared. That's just an example using the comparison theorem. That's not the cool part. Every teacher that teaches this does this one. It's even, I'm pretty sure it's even in the book. It's called Gabriel's horn. So our next example is going to be Gabriel's horn. But I want to make sure everyone has what they got in here. You all ready? Kenneth, are you ready? You're writing, but you haven't looked up, so I don't know if you're taking notes or. Not Kenneth, Michael.
Yeah, sure.
Why the fuck am I calling him Kenneth? His last name's like Kenneth. That's why. He said, yeah, sure, I can go. Okay, so Gabriel's horn. Region R is bounded by y equals 1 over x and the x-axis. The x-axis on 1 to infinity. R is rotated around the x-axis. To form an infinite horn. So this is rotated around it. One over x never crosses nor touches the x-axis. So that's why we call it an infinite horn. It's just the horn, the radius of the mount, the horn part is getting smaller and smaller and smaller and smaller and smaller. That is the worst fucking. Oh well, fuck it. Can't do it. Do it now. We will show this horn if filled with paint. Holds a finite amount. But there isn't enough paint to paint the surface area. You can hold paint, but you can never paint it. It's a little bit of a mind fuck. Well, this takes us back to chapter 6, doesn't it? Surface area and volume. So the volume of a given disk here is going to have a width dx. And the radius r is y, which is 1 over x. And the disk will be a 2 pi r. Nope. Area. I'm doing area. To do the volume, we need area. So dV is going to be the area times the dx. That gives us some height. And the area of each disk is pi r squared, but r is y, because that's my distance up. So pi times 1 over x squared dx. And that means the volume is going to equal 1 to infinity of pi over 1x squared dx. So here we're finding the volume. We're going to rewrite that. We're going to use like a dummy variable. I'll use a b here. Limit as b goes to infinity, 1 to b. Pi x to the negative 2 dx. We already knew this converged from the P-series test we just talked about. P was greater than 1, so this is gonna converge, it's gonna give us a value. We go up a power, divide by the power. We've got negative pi times the limit as b goes to infinity. This will be negative 1 over x from 1 to b. So negative pi times the limit as b goes to infinity of 1 over b. And then we've got minus 1 over 1 is 1. So as we evaluate b going to infinity, this thing goes to 0 and we end up with pi. So it holds the volume of the horn is pi cubic units. There's your disk method brought back to you as a nice little fresh reminder of chapter 6. Now we'll do the surface area. I'll give you another minute to write this down. All right, so if I got my picture up there, I'm gonna keep the picture there because it helps. The surface area, remember, is we're looking at 2 pi r ds.
It's like,
Yes. And r is in terms of y here, so this is 2 pi y, which means but we got y in terms of x, so we're going to treat the ds. We're going to do this as 2 pi times 1 over x ds. And here this will be 1 plus dy dx squared dx. So this is our dA. So what happens there? We've got 2 pi times 1 over x. Y was x to the negative 1, so dy dx is negative x to the negative 2. So dy dx squared is x to the negative 4th, or 1 over x to the 4th. The negative gets squared out. The 1 is the coefficient, but the 1 in the exponent remains. So this is 1 plus 1 over x to the 4th dx. And we're going along dx, we're doing 1 to infinity here. So now if I put the integral in, we're looking at the area now. Surface area. This might be a little bit easier to look at if I do 1 to infinity, 2 pi, 1 over x, and I get a common denominator inside. So I've got x to the 4th plus 1 over x to the 4th dx. Yeah. This, I took the derivative, brought the power down, lowered the power by 1. You know, like x to the n, when you do the derivative is nx to the negative n minus 1. Don't. Okay, it's all good. I got a square root on bottom. This is square root on top and bottom. The square root of the bottom is x squared. So I can pull out a 1 over x squared and just write this as this. So cleaning that up, I've got 2 pi over x cubed, x to the 4th plus 1 dx. And you may want to try to do a u sub, but the x cube's on bottom, it doesn't work. But the square root of x to the 4th plus 1 over x cubed, how does that compare to the square root of x to the 4th over x cubed? The top's a little bit bigger on this one, right? The denominator is the same, which means this one's got to be slightly bigger than that one. So if this diverges, then this diverges. And now I'll put my limit in. I'm doing limit as t goes to infinity. Put my 2 pi on the outside real quick. 1 to t. This is going to be x squared over x cubed when I take the square root of x to the 4th, which is just x to the negative 1. Or 1 over x. You're more used to seeing it as 1 over x. What is the integral of 1 over x? It's yeah. It's going to be natural log of the absolute value of x. And I'm just going to do them right away. I'm going to do the natural log of absolute value of t minus the natural log of absolute value of 1. So I'm skipping the whole natural log absolute value of t from 1 to, or natural value of x from 1 to t. We're going to this. Natural log of 1 is 0. But natural log of infinity, this diverges. And since this diverges, so does the integral from 1 to infinity of 2 pi over x cubed square root of x to the 4th plus 1 dx. It will take an infinite amount of paint to paint it. Infinite amount of paint to paint a horn that only holds pi cubic units of paint. So the surface area is greater than the volume.
Love this chapter already.
Isn't that kind of neat? I don't know that it's useful, but it's kind of neat, right? You have something that holds the volume, it holds an actual amount, but you don't have enough paint in the world to fucking paint the surface of it.
Yeah,
that's deep. It's only because we have shit going to infinity on the horn, so you couldn't actually make a physical horn that does this, right? So this is not a real horn.
That's why it's Gabriel's.
That's why it's Gabriel's horn. It might have been written by somebody named Gabriel, probably. That would be my assumption. All right, that's 7.8. If you want to glance over 7.6 to see some fun miscellaneous intervals, I might make a video about it. It's in the book. It's not going to be on your test. 7.7 does come up later. I want to say it's Newton's method. I'm moving that to another section because it fits better in another section. And so this is what your test will be on. It will not be Wednesday because that would be a dick move. You don't have time to really like study this last section. So the test will be next Monday. On Wednesday, we're going to start up chapter 9, which will not be on the test. And other than that, have a good day. Get the fuck out. Later.